Hey everybody, Mr. Judson here. So today in calculus we want to talk about this idea of a function and its continuity. Is the function continuous? And even though we're going to go through this definition here in just a minute, and you can pause at any point to write this down, but here's the main idea. A function is continuous if you can draw the whole thing without picking up your pencil. That's really what we're getting at today, okay? Now we've got a way to define that mathematically. And so what we're saying is this. F of x, so some function, could be anything, a line, a parabola, cubic function, square root, is continuous at a certain value c. Okay? C can be anything along that function. It's continuous if the following three conditions happen. So number one, f of c is defined. That means there's an actual point there. There's no asymptote. There's no hole in the graph. It's defined. It's a point on our graph. Okay? The limit as x approaches c of some function exists. There's actually an answer to it. We don't do the limit and get does not exist. Okay? So the limit exists. And it would have to exist if there's a certain point that exists on the graph. We could actually do this limit with direct substitution. Okay? And they even go one step farther and say that the limit of f of x as x approaches c is in fact f of c, which means we did direct substitution and got an answer. And so really the only way these things could not happen is if we have an asymptote or a hole in the graph. Those would be breaking points which would make our function discontinuous. It's disconnected, all right? And so that's kind of the idea that we want to look at for today. So let's just draw a couple quick pictures of some examples of functions that are not continuous. So here's my first one. I've got some function that goes like this, and there's an actual hole in the graph right there. Okay, so I would look at that and say there's a hole in the graph right here. I could not draw this function without lifting my pencil, and so it would be discontinuous. There's my abbreviation for that. Now, just in case anybody's thinking this way, well, I could draw this. I could come down here, make a little circle, back trace, and then continue to go. I didn't lift my pencil, Judson. There you go. Well, no, that doesn't count. If we were doing this on the graphing calculator, we wouldn't see that little circle. We would just see an empty spot, and the open circle is something that we just placed there so that we know what we're talking about. Okay? So we're discontinuous at that point. Here's another example. There's my asymptote, and I've got a function that goes like this, and on this side it goes like this. And this function would not be continuous because, these two curves would never connect up here. They get really close to this line without touching. Now, somebody could say, but Judson, on my graphing calculator, if I zoom in on this way up high, like where my y value is 1 billion, they're so close it looks like they touch. Well, it looks like it, but we know it doesn't, right? They would never connect. And so this function would be discontinuous at that x value. Anytime we describe where a function is discontinuous, it always has to do with the x value, not the y value. Okay? So if this was x equals 1, I would say this is discontinuous at x equals 1. If this was at x equals 2, discontinuous at x equals 2. Okay? And then of course, if I had an example that looked like this, here's one curve that comes down. Right here I've got another curve that goes back up. And there's obviously some space in there. Those two curves are not connected together, and so we would say that this graph is discontinuous, okay? At whatever this x value is. So if I just make that x equals 2, I would say this is discontinuous at x equals 2. Right? So a hole in the graph, asymptote, or maybe a piecewise function where those two sections don't touch, that would be considered discontinuous. All right, so I want to just kind of clarify one thing here. If I was able to take this curve right here and slide it down to the point where that open circle got filled in by the other piece, now that function would be continuous. Okay? So in a piecewise function, even though we've got an open circle on one side and a solid dot on the other, if that solid dot sits inside the open circle, that is considered continuous. Sometimes people think, well, wait, if it's an open circle, you never really get to that point. But you do because you get to it on this side, all right? So that would be a continuous function. That was not the case with my original picture, so I'll go back and leave it like this. So here's an example of a question that we could get asked today. Discuss the continuity of this function. And so when they say that, discuss, what they really want us to do is to write down, where is this function continuous? I can see that there's a hole in the graph at x equals -2, so we're discontinuous there. I can see there's an asymptote at +2, so we're definitely discontinuous there. But aside from that, this function is continuous everywhere else. I could draw this whole part of the function without lifting my pencil. I could come over here and I could draw this part without lifting my pencil. And I could draw this. All right? So, and when they say discuss, that doesn't mean sit there and have a discussion with yourself. They actually want us to write it down. Okay? So I would say that this function, I'll just call it f of x. F of x is continuous on the intervals -infinity all the way up to -2. And remember, we'd write that last year like this. Interval notation. So a parenthesis means don't include that value. If we've got brackets, that means do include that value. So this is not the point -infinity comma -2. It's an interval on where this function is continuous. And whenever we talk about intervals relating to a function, it's always x values that we write down. We never write down y values unless we're describing the range of the function, as in domain and range, okay? So this function is continuous from -infinity all the way up to 2. Got an open circle, so that's why I have a parenthesis there. And then from -2 to +2, still using parentheses because we got an open circle on this side and an asymptote on this side, and then from 2 off to infinity. And just as a reminder, we never attach a bracket to infinity or -infinity. If we did that, what we're doing is we're saying that you can actually get there. But you can't, because as soon as somebody picks a really big number, somebody could always add 1 and get a little bit larger. Okay? There it is. There's my answer. I have discussed the continuity of this function. All right, so you guys go ahead and try this one. All right, so obviously there's a break at x equals 3. I could draw this whole part without lifting my pencil, and I could draw this part. So I would say that this function, f of x, is continuous on the interval from -infinity to 3. Open circle, so I've got a parenthesis there. Here I have a solid dot, so on this part of the graph, I want to make sure I put a bracket where the 3 is. So from 3 on to positive infinity. So continuous on this interval and the interval from 3 to positive infinity. That's where this function is continuous. All right, so this question, it says, find all discontinuities in this function. Where is this function discontinuous? You guys tell me. Well, if we think about what we know so far, we know that a function is discontinuous when there is a hole in the graph or an asymptote. And so I just need to see if those exist. And so the first thing I want to do is I want to factor this denominator. So I would have x minus 1 over, this would be x times x. Two numbers you multiply to get 2 and subtract to get a positive 1. That would be a positive 2 and a negative 1. And so I can cancel these factors, but what I have to remember is there's a hole in the graph. All right? If I was going to actually graph this, I would want to do that. But if all I'm trying to do is just say, where is this function discontinuous, I see what makes the denominator equal 0. Whether it's a hole in the graph, because those two are the same, or if there's just an asymptote. I don't really care what's breaking the graph. I just want to acknowledge that it's happening. So f of x is discontinuous at x equals negative 2 and 1. Now, sometimes they'll talk about, is the discontinuity removable? Could you somehow remove this by assigning a point to where that open circle is, the hole in the graph? And so a hole in the graph is considered a removable discontinuity because we can cancel those two factors. All right? So a hole in the graph is a removable discontinuity. Okay, by canceling those, I'm now saying there's a hole at positive 1, and so that would be removable if I assigned a point to that hole. Now, how do you assign a point? You can do it with a piecewise function. We could say f of x equals this if x does not equal 1. And then our second piece is f of x would equal, let's see, if I put a 1 in here, I'd get 1 over 3, so 1/3. So in my piecewise function, I would say f of x equals 1/3 if x equals 1. So I now just filled in the hole, and that's what creates a removable discontinuity. Okay? Only holes are removable, nothing else. You can't take an asymptote and somehow connect the two pieces by putting a point in there. That doesn't work. Let's do another one. All right, so something else we need to talk about today is what's called a one-sided limit. Okay? Now, what we've said with limits is you always need to approach your x value from both directions and see what's happening. And our two answers have to agree with each other. If they don't agree, if we're going up to this number and this number down here, well then we'd say the limit does not exist. But what if I only want to approach it from one direction? What if I don't care about the other direction? You know, how would we say that? So if I wrote this down, the limit as x approaches c, some number, whatever it is, and I put a little plus sign where the exponent would go. That means I'm approaching that number from the larger side, so from the right, okay, of f of x. So we would say that this approaches c from the right. Or larger side. Okay? I don't really care which way we think about that, but it's coming at it from this direction. And if I say the limit as x approaches c, and I put a negative sign up there where the exponent goes, now I'm approaching it from the smaller side. Okay? And we don't need to come at it from both directions. When we see this plus or minus sign here, we only come at it from one direction. I really don't care what's happening on the other side. So this right here would approach C from the left, or smaller side. Okay? So here's a sample problem. All right, so they're going to have some problems like this where they give us a picture of a graph and then ask us a series of questions about it. So what is the limit as x approaches -2 from the larger side of this function? So I'm coming back at -2 from this direction. What are my y values getting close to? Looks like they're getting close to 4. So there's my answer. What's the limit as we get close to -2 from the smaller side? Okay, well now I'm coming at it from this direction. Getting close to -2. My y values are getting close to 4. So what's the limit as x approaches -2 of this function? Well, now since there's no plus or minus sign here, it means now I have to consider both directions. And the two answers have to agree with each other, which I can see right here they do. So answer's 4. Now if this was approaching 3 and this was approaching 5, then here I'd say does not exist. Right? Limit does not exist. And what is f of -2? I guess my graph doesn't extend high enough to be able to answer that, but let's just do this. So now I'm not doing a limit, I'm just saying what y value do you get when you plug a -2 in? And since it's defined as this point up here, then the answer to this would be 5. Okay? So as you write this stuff down, it's going to seem like, okay, there's my answer. Okay, didn't I just answer that? Okay, didn't I just answer that? But they're really trying to make sure that we get it, that we're coming from the right, here we're coming at it from the left, and here we're coming at it from both directions. Okay? And these two numbers would have to be the same to be able to write this answer down. And it would be the same as those. If these two numbers are different, then we're in a does not exist situation. All right, you guys go ahead and try this one. So, here's what's going to happen. We're going to look at this, we're going to go, well, if you put a 4 in there, it's undefined, so limit does not exist. But you have to remember, it's okay to get 0 in the denominator when you're doing a limit. We're trying to answer the question, what do the y values get close to as x gets close to 4, but this time we're only interested from the smaller side. Okay? So, I could still try to factor this and see if something cancels. I think I can do that. If I write it down this way, the limit as x approaches 4 from the small side. Oops. I've got the square root of x minus 2. And then if I factor this is a difference of 2 squares if I call the square root of this the square root of x. Right? If this was a 7, I could say, well, root 7 times root 7. So when I make my two parentheses, I'm going to have root x times root x. That does give me x. Square root of that's 2. So 2 times 2, one's positive, one's negative. So I have a hole in the graph So I can cancel this, and even though I'm doing a one-sided limit, this is still okay. And so now what I get is the limit as x approaches 4 from the small side of 1 over root x plus 2. And so if I plug a 4 into here, I would get the square root of 4, which is 2. 2 plus 2 is 4, and so my answer is 1/4. Now if somebody's like, I think I did it right, not 100% sure, you know, we could always go to our graphing calculator and graph this function and just do it graphically. Let's just see what happens. So let's see, f(1,8), we'll get rid of all this, and I'm going to put the numerator in parentheses. So the square root of x minus 2, close the numerator, divided by, and I'll put the denominator in parentheses as well, x minus 4. Okay? And I'm going to go zoom option 4. And so we're getting close to 4, but we're getting close from the small side. All right? So it does look like I've got a positive answer here. I can't really, you know, visually look at that and tell that that's 1/4. But I could go to a numeric method now if I want. I could hit my trace option, and I could say, let's try 3.99. Okay, so I'm getting close to 4 from the small side. 0.2501. Get a little bit closer. 3.9999. And that looks like it's even closer to 0.25. You know, so if I wanted to acknowledge that I did a numeric method, I can say here's the XY table that I get. I plugged in 3.99 and I got 0.2501 something. I don't remember exactly what it was. And when I did 3.9999, I got 0.25000. I don't remember how many zeros there were, but I got closer to 0.25. And so I'm just saying, yeah, that's 1/4. Okay, I did this 2 different ways. I did it algebraically, and then I came back and did it numerically. But I don't have to check 4.0001 because we're only coming at it from the small side. All right, so here's our homework for today. We're still week 5, so number 5 continued, day 3, because this is Thursday for us now. We're on page 83. I know you guys are going, oh my gosh, look at all that work. It's not that much. 2, 4, 6, 8, 10, 12, 13 problems. So anyway, we're doing 6, 10, 13, 16, 17, 21, 23, 27, 31, 35, 38, and 41 and 47. All right, there it is. That wraps up week 5. So this will all be due on Tuesday for us, all 3 days. And you guys have a good weekend. We'll see you on Monday. Take care. Be safe.